may think that that's exactly why you have your camera off, but you're really missing out if you can't participate all the time. Okay. All right, so what do you guys know about friction? Let's just sit and chat about it first. What do you guys know about friction? Anything? What is it? How does it work? How is it related to anything that we've done?
It's an opposing force.
Okay, it's an opposing force. Opposing what?
The motion of one object relative to another.
Okay. Awesome. Okay, what else? That's great. What else do you know about friction?
Not really a fundamental sort of force like gravity, etc.
Sorry?
It's not a fundamental sort of like force like gravity, I guess.
Okay. Yep. It's in that category of electromagnetic forces because it has to do with the electrons and atoms on the surface of the molecules. That's good. So it's not a fundamental force. Well, not one of those four. Okay, so it's part of those electromagnetic forces, just like most of our other contact forces. Awesome. What else?
The formula is the coefficient of friction times the normal force.
Okay, so Assad's thinking back to some stuff that he learned before. We have a formula, which you guys are going to want to learn eventually. Okay, so I'll go ahead and introduce that now since Assad's brought it up. So we've got the force of friction. And force is a force just like all the other forces. So it'll be in newtons, just like your pushes and your tension and all those other forces. It's just going to be similar to all of those. Okay. This letter is mu. It's a Greek letter, kind of like pi or theta or something like that. You've seen it before. They use it for the coefficient for like micrometers and things like that. This is not that. It's the same letter, but this is what we call the coefficient of friction. All right. And then of course the normal force between the two surfaces. All right, so we'll be using that today. We'll talk about that. Awesome. Anybody else? Anything else that you have seen or you know about friction or anything else we can kind of add into our list here?
I was gonna say reaction force, but it's the same as opposing force.
Okay, all right. I know you're talking about reaction force. You know, this will, Newton's third law will apply to friction just like anything else, right? So when one object has friction with another object, there will be a frictional force in the opposite direction on the first object. So just like that, we'll continue to have Newton's third law applying here. Okay, cool. Anybody else? All right. How about, let me ask this. It was mentioned that it's an opposing force between two objects. It's during the relative motion of two objects. Do two objects have to be moving in order to have friction?
Yeah, I think so because um, the only way friction happens is if. Well, actually, I don't have any reasoning. I just think it's right if it is moving that it has
Okay.
friction.
All right. And we've talked, we talk about friction a lot of times in that way where when things are sliding against each other, there's that rubbing, which is friction. That's a type of friction, which we call kinetic or dynamic friction. Kinetic and dynamic both have to do with motion, so. Okay, so kinetic or dynamic friction is when two objects are sliding or rubbing against each other, right? So that's the kinematic or dynamic friction that we're used to. That's very similar to your fluid frictions like air friction and things like that, though we kind of categorize those a little bit differently just because when we talk about kinetic or dynamic friction, we're usually talking about two surfaces sliding against each other. When it's going through a fluid, it's happening all around it. And so we kind of separate those. So we also have that kind of fluid friction, air friction, water friction, all of that we call fluid friction. Okay, so that's like your air resistance and things like that. Okay, let me ask this. If I sit here and I push forward on my iPad, and I'm actually pushing on my iPad right now. I'm trying to push it towards you guys. When I push on it, why isn't it sliding?
Maybe you're not putting enough force to actually move the object.
Okay, but what do you mean when you say there's not enough force to move the object?
Because for you to be able to move the object, you need to put enough force that surpasses the weight of the object and in how much force it pushes back onto you.
Okay, I'll come back to that. Dan's raising his hands. What's up, man?
There's more. You have to put as much force compared to the amount of friction that there is on the object. So you have to add more energy. You have to push harder for the object to move.
So Dan, are you insinuating that there's friction even though the iPad isn't sliding?
Yes, because otherwise the object would fall. It could, if there was a slight movement, the object could fall off the table. If the table wasn't perfectly straight, it would slide and fall off.
Good point. What's up, Liam?
Well, I was thinking, the natural, the first thing you would think if something has more mass, then it would have more friction and be harder to move across the table. But I was curious about one thing. Let's say like, I don't know, your cup was sitting on the table and it was lighter than the other one, but it was like super sticky on the bottom or something, where would I guess you'd say like third party factors like the stickiness and all that, where would that play a part in it? In like the friction and stuff.
Good question. In a course like this, in an introductory physics class, we'd probably just kind of classify that with resistance, right? Which we would say is kind of friction. Sometimes we use the words friction and resistance interchangeably. So in a class like this, we'd probably just say it has something to do with the resistance of, something being sticky. As you get into deeper physics, you would recognize that the reason why something's sticky is because of surface tension within whatever is the sticky thing, whether it's glue or honey or sugar or whatever it is that's making it sticky. when you try to pull that, there's some surface tension actually inside of that honey or syrup or whatever it is. And that tension is the force. So you could refer to it as tension, or you could refer to it more simply just in this class, we're okay with just saying it's just another form of resistance. All right, so let's talk about, you know, Assad and Dan. That was a great question by Liam, a kind of an introduction into different types of forces, kind of identifying how we're simplifying things here. I want to go back to what Dan and Assad were talking about with respect to the forces on the iPad. Can we draw a free body diagram for the iPad when I'm pushing on it? So I started drawing it already. This block right here is my iPad. So what are the forces on it? If it's not moving,
Gravity.
Okay, so we've got the force of gravity down.
Force of Mr. Bywater.
Force of Mr. Bywater, so we're going to say that I'm pushing it over to the right. That's actually a normal force, right? It's a contact force. It's a normal force perpendicular to my finger. I'm just going to go ahead and go force of B, so force of Bywater. What else?
Force of friction. Away in the opposite direction than Bywater, the normal forces.
So even though it's not moving, there's friction there?
Yes.
Okay, because we got this normal force up, right? So for those that are having a hard time picturing friction without motion, think about this. If there's no friction, what do you see in the picture? What would happen if there was no friction?
The object would move to the right.
It's got to accelerate, not even just move, it's got to accelerate to the right because there is an unbalanced force. And that's what Newton's first and second laws tell us, is that when there's an unbalanced force, there has to be acceleration. So the only answer is that there's something in between the contact of the table and the iPad that allows for some type of frictional force in the opposite direction, even though it's not moving. Okay, this is a different type of friction. We mentioned this, the kinetic friction, the sliding, the dynamic friction, right? We talked about the fluid friction as it's going through the air or water or something like that. This is a different type. This is what we call static. What's that? Lily the zipper breaker. All right, static friction. Sorry, it's broken. It will go back on. All right, static friction is a friction that occurs when two objects are at rest, but trying to move. Like in the case of the iPad. Right? When I push on it, it's going to try to move because there's a force, it has mass, therefore it should accelerate. So it's going to try to move, but there's something in that contact between the iPad and the table that causes a frictional force that opposes that motion. All right? Or that attempt at motion. Okay? And this is often a hard part of friction, is recognizing that there's two different kinds. One when it's at rest and one when it starts sliding. All right. You may have, yeah, Ali, what's up?
What if the frictional force was larger than the Bywater force? Would that mean, but the object wouldn't move, right? Okay,
good question. And that's one of the things that usually comes up. We can talk about it now. So with static friction, okay, Static friction has a maximum possible force. All right, because when my iPad is just sitting here at rest, there doesn't need to be any friction. So friction is 0. If I push lightly on the iPad, just barely touching it, then you're right. It doesn't need its maximum value of friction. It only needs enough to counter my push. Friction is not an active force that starts just pushing against. It's a reaction. Somebody mentioned this. Was it you, Ollie, that mentioned that it's more of a reactionary force? Somebody mentioned, maybe it was Alex, I don't remember. Somebody mentioned it being a reactionary force. And it is, especially in the case of static friction, right? Assad mentioned this equation up here earlier of friction equals the coefficient times the normal force between the two surfaces. For static friction, it's actually more like this, that friction is less than or equal to the coefficient of friction times the normal force. So it can have up to a certain value, but it can also have anything less than that if it doesn't need to be at its specific value, right? You've probably felt this before. If you're trying to move something that was really heavy, I felt this a lot in the last 2 weeks that as we've been moving houses, is that as you try to push on something, right, at first it doesn't budge, right? And as you start to exert more force, and obviously friction builds to match the force that you're giving, at some point, I'm able to push harder on the box than friction is able to do. So at some point, as I'm pushing, I overcome that static friction. I overcome that ability of friction to resist. Once that happens, it stops being static friction and starts being dynamic friction. And anybody that's ever done that before has likely noticed that when you start pushing on something really hard, as soon as it starts moving, it's usually easier to keep it moving than it is initially. Sometimes when you push on something, you kind of stumble a little bit as it starts to go. That's because static friction is usually stronger than kinetic friction. The force required to get it started moving is going to be larger than the force required to keep it moving. All right. Any questions so far? Any other thoughts or whatabouts or anything like that with friction?
Just on that last part, is it easier to move because of momentum, or is it just because the kinetic friction is so-called weaker?
It has more to do with the mechanics. We're not going to touch on momentum yet. We'll do that very, very soon. We'll start talking about energy and momentum and things like that. Let me just draw a picture for you right here. Friction works because surfaces, even if we feel like it's a really smooth surface, at the atomic level, surfaces are not smooth. Right? Surfaces are rough. They look kind of like this guy up here at the top where this is the surface, and it is kind of rough. When I match that up with another surface that is also kind of rough, you can imagine how the teeth from the upper one can get caught up in the teeth on the bottom one. And when it's just sitting there, the teeth kind of settle in. And so when you push on it, you can't get it going until you're able to get those teeth to kind of be unlocked with each other, those rough surfaces. And so that is harder than once it starts moving, it doesn't really have time to settle back down into that initial place. And so once you get it moving, it just kind of slides along the top. There's still friction in between those rough surfaces, but because it's not fixed in place and because it's not fitting quite as well, then it's going to be easier to get it to move. So it's more due to the mechanics of the two surfaces and less due to mass or inertia or anything like that, or momentum. Yeah, good question. Other questions?
Mr. Bauer,
What's up, Dan?
why is there no S in the top equation next to the M, but in the bottom one there is?
So the only reason for that, this up here, the top one, is the general equation for friction. All right. So the general equation can work for really any type of friction, but this coefficient will change. All right. Just like we just said that static friction is usually stronger than kinetic friction. Well, the normal force here isn't changing. So the only thing that can change is the coefficient of friction. And so you will generally be given two coefficients. One will be for the kinematics, so that we'll say the force of friction equals the coefficient of kinetic friction times the normal force. And then you'll have a second coefficient of friction. The equation's basically the same. The difference is that you might have different numbers. Because of what we just talked about, it's easier to keep something moving than it is to get it started moving in terms of the friction. So this friction down here tends to have the ability to be larger. The other thing is with the kinetic friction, anytime two things are sliding, friction is constant. It doesn't become more or less based off of your speed. Now, we're not really talking about fluid friction here. That's a whole nother story that we're not even really going to worry about this year. We're going to focus mostly on friction between two surfaces. So kinetic friction is always equal to, and then static friction, we were talking about, you know, depending on how hard you push on the object, could be equal to, but it could also be less than what it is fully capable of. And so that's why I had put an S down there, just to remind us that this one down here is static friction, whereas the other one is more of a general formula for types of friction. Other questions? All right, let's do this then. I think we're about halfway through class. So I'm going to go ahead and give you a break. So we've done our talking discussion part. I'm going to give you a break now. You can have 3 or 4 minutes. Please get away from your screen. Get up, stand up, walk around. I am too. I'm going to go check on my daughter. When I come back, we're going to work through at least 2 problems dealing with friction so that you can see how it connects to everything that we've been doing for the last week and a half, 2 weeks. All right? Okay, I'll see you in a few. All right, everybody, start coming on back. All right, thank you, Ola, Assad, Ali, Asta, for turning on your cameras. As you come back, please do turn on your camera so that I know that you're here, or at the very least, give me a green check or thumbs up in the participants window. Thank you, Dan. Thank you, Sean. Thank you, Wasim. Guys, either video's on or give me a check in the participants window. If I don't have it in 30 seconds, then I'm going to count you as missing for the second half of class. I understand if you can't turn the video on, but you at least need to give me a heads up. Let me know that you're here. Thank you. Okay, so Alex, Nicholas, Zara, you are not here. I'm going to put in that you are missing the second half of class. All right, here we go. Let's work through an example. We'll do a couple of examples. We'll start with, let's do a simple one. Let's start with a block on a table. All right, so here we go. We got a block sitting on a table. And I'm going to exert a force on it. To make it a little bit interesting, let's go ahead and make it, I'm going to exert a force at an angle. Okay. I'm going to exert a force kind of like this. Let's say the block has a mass of 5 kilograms. And then the force that I'm exerting is a force of 30 newtons. And we are going to calculate all right, thank you, Assad. All right, so we're going to calculate the necessary coefficient of friction so that the block will not slide, okay? Calculate the necessary coefficient of friction. All right, and this is going to be static because it's not sliding. So calculate the coefficient of friction necessary so that the block will not slide. That's fine, Nicholas. Just give me a check next time, buddy, so that I know you're here. All right. So here we go. Just like all of the other questions that we've been doing recently, okay, we're going to start with a free body diagram. All right. So here's my block. Sama, name a couple of the forces on the block. In what direction? Sama, are you there? Can you give us a couple of forces?
Gravity.
Okay, force of gravity. What else? Give us one more, Sama.
Friction.
Friction, okay. Which direction is friction gonna be?
Left.
Yeah, good, because I'm pushing it to the right. If it's not gonna move, there does need to be some friction over to the left. Perfect. All right. Jed, what are some other forces going on here?
Some other forces is you actually pushing the block.
Okay, so the force of me, so down like this, which I just labeled as F earlier. Okay, awesome.
And the normal force upwards from the table.
Okay, and the normal force upwards on the table. Awesome. We're going to go ahead and give this guy an angle. We'll give him 30 degrees just because, no, we're not going to use 30 because I just used 30 for that may be confusing if you go back and look at it later. We'll go 20 degrees is the force there on the block. Okay, awesome. So now we need to do our forces. Okay, now the question wants us to find the coefficient of friction here. And so that is a horizontal force. So let's look at the horizontal forces and see if that will allow us to find the force of friction and therefore the coefficient of friction. All right, so the horizontal forces here. Yeah, Ali, what's up, man?
I might be wrong, but I think you said that friction is a reaction force. So doesn't that mean that friction has to go in an opposite direction as the force that you're pushing it?
Yes.
Okay, but then if the block is not moving right now, then shouldn't the frictional force be diagonal upwards?
Okay, so good question. No, because friction can only work parallel to the surface. Okay, friction can't work pushing up. Friction will never push something up off a surface, right? Friction doesn't pull something down into a surface. Friction always works parallel to the surface. Okay, now when I push down on it, that is going to change some things, right? It should change the amount of friction because friction depends on the normal force. And when I push down, the table is going to have to push up harder. So there are going to be some connections, but the friction itself can only actually exert a force parallel. So it is reactionary, but it's only reactionary to the part or the component of the force that is parallel to the surface, which is what we're going to look at right now.
Okay.
Dan, what's up, man?
Why do you need the angle for the force?
Good question. Good question. And the reason is really the same thing that I was just talking with Ali about, right? When we look at friction, friction only has to oppose the motion that is in its plane, the motion that's in the same direction as it, right? Pushing up or down on something isn't going to cause more friction by itself, right? Right now, as my iPad sits here, there's no friction, right? There is no friction because it's not trying to move. If I push down on my iPad, there's still no friction because it's not trying to slide. There's no attempt at motion, right? In order for friction to take place, kinetic friction will happen if it is sliding. Static friction will happen if it's attempting to slide. Otherwise, none of those other forces matter when we talk about friction. Does that make sense, or you got to follow up? Okay, so that's actually what we're going to look at right now, because what we're going to look at is the horizontal forces here. Okay, we haven't done a lot of balancing vertical and horizontal, but in this situation, that's one of the reasons why we're going to do this question right now, is in looking at the force diagram that we created together, right? Friction is definitely in that horizontal direction. parallel to the surface of the table. Are any of our forces in that same direction? Parallel to the surface of the table. Do we have any forces that are parallel to the surface of the table other than friction?
No.
Not purely, right? Not purely. However, we learned about components. We learned about vectors, right? This force vector right here, the one of me pushing down on the block, it's not straight up and down. It has a component or a piece that is in the horizontal direction. All right, a part of that force is horizontal. All right, so what we need to do is we need to break this up into a horizontal piece and a vertical piece. All right, and we're not going to make this too complex. We're not going to have like 5 vectors going in all sorts of different directions, but we do want to make sure that we're able to take a single vector and break it up into 2 pieces like we learned in the first unit. Okay, so we're going to take this force vector and break it up into the horizontal and vertical pieces. And this, Dan, answers your question in why do we need the angle? Well, the angle is going to allow us to find how much of that force is horizontal and how much of that force is vertical. All right, so I'm actually going to redraw that force, just that one over here on the side. Right, it has a magnitude of 30 newtons, and then the angle is 20 degrees, right? So if we break it up into vertical and horizontal here, the angle here is 20 degrees. You know what, I can draw that bigger. We can draw that bigger. We can do better. There we go. So it has a down component and it has a component to the right. There's our 20 degrees, 30 newtons. All right, so we're gonna go ahead and find the components. All right, let's find the horizontal component because that's actually what I'm interested in right now. I need to find out the forces that are in the same direction as friction. Remember, everything horizontal is independent from anything vertical. Okay, we learned about that when we talked about the kinematics and things going vertically and horizontally, that things vertical are always independent from things horizontal. You can drop a ball and shoot a ball and they land at the same time because that horizontal motion is independent of the vertical motion. All right, so we want this side right here. So we need a trig function. Okay, you know your SOHCAHTOA. If you don't, then ask me about it. I'll show you a couple of videos that you can refer to remind you about SOHCAHTOA. We've got the adjacent side and the hypotenuse, so we want cosine. So cosine of 20 degrees is equal to the adjacent side, which is that horizontal piece that I'm looking for, okay, over the hypotenuse, which is 30. And we can solve that. We can multiply both sides by 30 and we can say that x equals 30 cosine 20. Go ahead and plug that into your calculator for me real quick. Let's get a number so we don't have to keep writing trig functions down.
I got 28.2.
28.2. Anybody else? Got that? Ola, got that? Got that? Okay. So 28.2. So that's the horizontal piece. And that's what we're looking for right now. So we're not going to worry about the vertical piece right now. If we need to, we'll come back to it. So now we can do Newton's second law for our horizontal forces, right? We've got friction, which is going to the left. Remember, Newton's second law says that the sum of the forces equals mass times acceleration, right? So the horizontal forces here are friction, which is going to the left. So I'm going to put negative friction. And then the force that we just found, which is the horizontal piece of my force pushing down on the block. And so that would be plus the 28.2 equals mass, which was given to us, right? 5 kilograms times the acceleration, which we said we wanted to stay at rest. So no sliding, so 0. That should allow us to solve for friction, right? We just move the F over to the other side, and we know now that the force of friction needs to be equal to 28.2 newtons. That hasn't answered the question yet, but it did give us the force of friction.
Isn't it negative?
No. Well, yes, it should be. I made it negative here, and which is why I got a positive value there. So yes, if you're going to say it's to the left, you really should say yes, it's to the left or negative because it's a vector. Yep. Yep. If you want your answer to be negative, then don't put this minus here. Sorry. You cannot put that there, and then your answer will be negative because you're just adding the forces up. All right, so how do I get the coefficient of friction? Jed, how do we get the coefficient?
I'm not sure, but yeah, I don't know.
It's the formula that we presented on the previous page. There's a formula that connects the force of friction to the coefficient of friction.
Oh yeah, it's like F is equal to MSF, I think.
It's there in your notes, right, Jed?
Yes.
Good.
Oh, FN because it's normal force, that's not bad.
There you go. Okay, so the force of friction is equal to the coefficient of friction times the normal force. So we know the force of friction now. Okay, the force of friction is that 28.2. All right. And anytime you use this, because friction is going to be one direction and the normal force is going to be the other direction, then when we put the numbers in, we don't worry about the negatives. You could do this. You could make your formula be this if you wanted. That may simplify things a little bit. Make it the absolute value. Just put in the positive numbers. The reason again being because the directions are going to be perpendicular to each other. Friction is always parallel to the surface, and the normal force is always perpendicular. Then the pluses and minuses really don't mean anything anymore because they're perpendicular to each other. So we'll go ahead and put it in the 28.2. But we don't have the normal force yet. So how do we find the normal force? Yeah, Assad?
You just said the normal force is perpendicular to the force of friction. So with the little triangle we created at the top right, with the 30 degrees being the hypotenuse, you would use sine to find the vertical component.
Okay, that'll certainly be part of it. Is that the only vertical force?
No.
So what are the vertical forces? Here we did the horizontal forces. So now we're going to look at the vertical forces. So what vertical forces do we have?
The normal force that is the table and the block.
Okay, so we've got the normal force, which is what we're looking for. That's what we need, right? If I can find this normal force, I can put it in and I can solve for the coefficient of friction. Awesome. What other vertical forces are there?
Gravity.
Gravity. And we know what gravity is, right? Gravity is going to be negative, and then it's going to be the mass times G, right? The force of gravity is always mg, where G is 10 meters per second squared, right? We were talking about mass and weight last class. Weight is always mass times the acceleration of gravity, or what it would have been if we were allowed to free fall. All right, so we got the normal force, we got the force of gravity there, and then as Assad mentioned, we also have this vertical component of the force, and so that needs to be added in as well. Okay, so we're gonna have to find that side over here. And so we're going to need to use our trig again. That's the opposite side and the hypotenuse. So opposite hypotenuse is sine here. So we'll go sine of 20 is equal to the opposite side over the hypotenuse. So 30 sine 20 equals y. Go ahead.
10.3.
10.3.
Yeah, I got the same.
All right, I'll give people a minute because I know other people still punching it in. Make sure you got that. Ola got it. Awesome. And that is also down, right? So we're going to add in another negative 10.3. And that should equal the mass times the acceleration, right? This is still Newton's second law. This is still sum of the forces equals mass times acceleration. But this time we have the normal force up. We have the weight or the force of gravity down. And we have the overall force in the y direction down. And of course, the acceleration.
So in these equations, does the negative 10.3 and the negative mg, is the negative the direction or is it like actually a value?
Yes.
So it's just direction.
And the value, I mean, it's a vector, right? So it has to be in an opposite direction to the positive, right? The negatives, if you add negatives together and you add a positive to it, it's got to go back to 0. So the answer is yes, it's both the values and the direction. It's important for both of those, otherwise it won't work. What's up, Liam?
I'm just curious, are we still doing all of this just for the coefficient? Like, I feel like this is pretty long for that, just that. I don't know.
Yeah. Yeah. But what I want you guys to realize is that we didn't know that from the beginning, right? What we did in the beginning is the same thing that you should always do. And I know you look at this and at the end you're like, whoa, that was a lot of work. But we didn't say at the beginning, I need to do this and this and this and this and this and this and this. We didn't say that, right? At the beginning, what we said is we need to find the force of friction. Okay, how do we find the force of friction? Well, we draw a free body diagram. We've been doing that for 2 weeks. You should be able to draw a free body diagram, right? And we said, okay, now that we have a free body diagram, I need to find the force of friction, right? So in order to find the force of friction, what did I do? I did F equals ma, which is what we've been doing for the last 2 classes now, right? We spent at least almost 2 hours now working through questions where we did some of the force equals ma. So it's not a new step. There's nothing new there. This is something we've been doing all along, right? And so we do the sum of the forces, we solve for the force of friction. We say, okay, now that I got the force of friction, I'm gonna put it in so that I can solve for the coefficient. And then we say, ah, dang it, but in order to get the coefficient, I need the normal force. So what do? We do something we've been doing for the last 3 classes. We do free body diagram, and this time we look at the vertical forces, right? So then we look at the vertical force, and that's what we're doing. Now we're doing exactly the same thing that we've been doing for the last 2 or 3 classes, trying to find the normal force based off of the vertical forces. All right. So I guess what I want you to recognize is that as we're going through this, we're not saying I have to go through 25 steps in order to get the answer. We're saying I'm going to do free body diagram. And then I'm going to do Newton's second law, sum of the forces equals ma, right? And if you do it one step at a time, then it's not as overwhelming as from the beginning saying, oh my gosh, I got to do all this stuff. On a celebration, it would let it, you know, part A would be draw the free body diagram. Part B would be find the force of friction. Part C would be find the normal force, right? Part D would be find the coefficient. I'm not going to give this to you just in this form and say, okay, let's, you know, you need to be able to work all the way through this. So I'll step you through it, right? By each of those individual steps, you should be able to do. Does that make it a little less scary? Hopefully. It can still be a little intimidating, but as long as you can do each individual step, then you'll be okay. Has anybody solved for the normal force there? You should be able to solve for it now. You got all the numbers in there. So you add the 10.3 to the other side, add the 50 to the other side.
The negative force of gravity, wouldn't it be would be positive 10, right?
Force of gravity is mg, right? So g is 10 meters per second squared. The negative on there is only to show direction.
Okay.
So as long as this number is negative, it doesn't matter if you put it on the 10 or if you put it somewhere else. But that overall number needs to be negative because that force is downward.
Yeah, that makes sense.
Yeah, so I used the positive 10 and I put the negative on at the front just because I knew it was supposed to be downward. But you could just put plus and put a negative 10. Either way. I think somebody else was going to ask a question.
No, I was saying the answer for the normal force.
What'd you get?
60.3.
Awesome. So now we've got that number. We can put it in. We can go 28.2 is equal to the static coefficient of friction times 60.3 newtons. You divide by 60.3 and you've got your answer.
Four, six, seven.
6, 7.
4, 6, 8.
It doesn't have any units, right? You've already got newtons on this side, you've got newtons on that side, so the coefficient doesn't need units. Questions? Okay. Please note that getting the force of friction was not overly difficult, right? The force of friction we did here at the beginning. That was actually pretty straightforward. It was just looking at the horizontal forces, right? So the force of friction is not a new complicated topic, but it can complicate questions if you have to look. Really, the thing that complicated this one was the fact that we had a horizontal and vertical component of that force, which we hadn't seen yet. So I had to make sure that we saw that sometime today. Okay.
Mr. Bywater, is there nothing you put behind MS? Like, because we have newtons to measure the force, do we not put anything behind it? Sir?
No, it can't have any units, right? If you look at the formula, right, the force of friction, see if I write over here, F equals mu Fn, the force of friction here is in newtons, right? The normal force is also in newtons. If the mu has units, right? Like if you put meters on there, then it would say meter newtons and newtons are the same thing, which can't be the case, right? Newtons have to be equal to newtons. Any of your formulas, the units on one side have to match the units on the other side. And so the coefficient of friction is just a ratio that tells you how rough a surface is based off of, you know, how hard you're pushing on it, how much friction comes based off of the normal force. It's more of just a ratio. It's not really a, you know, it's not like G or something where it has a, you know, physical acceleration or something like that.
But how would you measure it then?
How would you measure it? Generally, it's knowing if you know the normal force, right? If we didn't add an additional force down, if all you had was the block sitting on the table, then gravity and the normal force should be the same. And then you pull on it and you measure the force required to get it to start moving. And so if you know that, that's friction. And if you know the normal force, then you can calculate the coefficient. Much like what we did here, right? We said, how hard do I need to push on it to get it to start moving? Well, that means that the static coefficient of friction has to be this. It could be more than that, right? It could provide more, but it needs to at least be this amount. Otherwise, it won't be able to supply the right friction. So similar to this, you probably just wouldn't apply an angular force. You just do a horizontal force. It's a little bit easier.
I don't quite understand the arrangement of the equation for F equals MA.
Okay, what's up?
Like, why is it equal to, like, there's one that's equal to 0, and there's one that's equal to MA.
It's always equal to MA, right? This was MA, but the vertical acceleration is 0. And so it's 0. Yeah, it's still MA. It's always equal to MA. Sum of the forces is always equal to MA. That's Newton's second law. This one was as well. 5 times 0. It was 0.
Okay.
Ali, what's up? I know it's time. If you guys want to go, that's fine. I'm going to answer questions. I know there's a couple of questions, but it is time. I'm aware of that. So if you want to go, you're free to go, or you can listen to the last couple of questions that are being asked.
Thanks, Mr. B.
What's up, Ali?
I'm confused. What does the coefficient do? So 0.468, what does that mean? What if it was 1? What does it do?
If it was 1?
Or what does 0.468 mean? I don't understand.
Well, it's just the relationship between the normal force between the two surfaces, how hard those two surfaces are pushing together, and how much friction can be applied between those two surfaces. It's just a ratio. You know, Dan was asking, well, how would we get that? Well, quite literally, you find the normal force between two surfaces and you pull on it and you find out how much friction can be there. And then you divide the two numbers, so you get a ratio. It's just a ratio. It's saying if I have this much force between my two surfaces, then there can be this much friction. Yeah, it's like saying, you know, if something weighs 20 newtons and there can be 10 newtons worth of friction there, then you can have half as much friction as it weighs, right? It would be 0.5. If it's 0.1, then the amount of friction is equal to the normal force.
All right, thank you. So if it was 1, what would that mean? That means that the friction and the force are the same?
The normal force between the surfaces, right? That's perpendicular, right? That normal force would be equal to the amount of friction that can be supplied between the two surfaces.
Okay.
Yeah,
Thank
it
you.
could be bigger than 1, right? There's nothing saying that it has to be less than 1, right? If you have a really, really rough surface, maybe the force between the two surfaces is less than the amount of friction that can be applied between the surfaces, right?
Yeah. Thank you. See you.
What's up, Liam?
I was just wondering that I'm just a bit confused because there was like a couple different formulas that were given, and I don't really know what the difference is. There was at the start F equals MF N, then there was F equals MK Fn, then there was F equals MA, and then last there was F equals MS Fn.
Okay, well, 3 of those are basically the same thing, right? That friction is equal to a coefficient times the normal force, right? The first one is the general formula for friction, right? But then depending on whether it's sliding or at rest, you use MS or MK, right? If it's at rest, you use the static friction, you use MS. If it's sliding, then you use MK. So that's those. The F equals MA is Newton's second law. That's what we've been using for the last few classes. So that's not new. F equals MA is just some of the forces.
All right, that makes sense. So they're like different ways to get the same answer, kind of. Those 3.
No, because they're different situations, right? The first one is the general situation. It says you get friction by multiplying the coefficient of friction by the normal force. Okay. The other 2 are like subcategories. It's saying, yeah, you multiply by the coefficient, but the coefficient is different if it's moving or if it's at rest. So the top one is just like saying, you know, this is quadratic equations. And then the one says, well, this is ones that you can factor. This is ones that you have to use quadratic formula on, right? They're both quadratics, but they're different scenarios. So all friction comes from friction equals mu times normal force. But any scenario could have 2 different coefficients. There's one, mu s, if it's at rest, because it's static, and there's one, mu k, if it's sliding.
All right, that makes sense.
Remember that the letter, the subscript is just a label. It's just a label. It's saying specifically this is the coefficient of friction we're looking at, the static one or the kinetic.
Thank you.
Anybody else? guess I can stop sharing the screen now. Okay. Cool. Thanks, everybody.
Can I ask something about the retake or like the error analysis thing?
Yeah.
The first thing I want to ask is, will I be able to schedule time with you after school to go over the questions?
Yeah, if you'd like to. Sure.
Is today okay?
Let's see. I have a student today from 3:30 to 4. I could do it at 4 if you wanted to.
Yep. And the second thing is, you said